Alright, this video deals with the question of dropping x with the equilibrium calculations involving equilibrium constant and the ice table and having x in the denominator. So we'll work with the hypothetical acid HA in equilibrium with H plus and A minus. And we're going to work with concentrations of HA being 0.10 molar. Second case will be 0.010 molar. Third case will be 0.0010 molar. And we're going to be given that Ka for HA is 1.0 times 10 to the minus 4. And our ice table will look like this. HA forming H plus A minus. Let's see for change. And we have, for the first part A example, 0.10, 0 and 0 is our initial conditions. Then losing x moles of HA, gaining x moles of H plus, and gaining x moles of A minus. And then when the system comes to equilibrium, the remaining amount will be 0.1 minus x moles of HA, x moles of H plus, and x moles of A minus. So the question here is, what is the effective concentration? And we want to write down the equation. Let me put another box, map out another space over here on the left, so I have this all on one slide. And so if we take the last line, the equilibrium concentrations, we know that the Ka, equilibrium constant 1 times 10 to the minus 4, will be equal to x squared divided by 0.10 minus x. So the issue of this little video is to decide whether and when it's appropriate to drop that x. And the issue is this x small compared to this number 0.1? And if it's very, very, very small, then it will be insignificant. When you do the subtraction, you'll get 0.099999, which will round up to 0.1. So we want to avoid having x in the denominator because we want to avoid doing a quadratic equation, which can give rise to lots of errors, lots of mistakes in the calculation, plus it's very time consuming. But for this video I'm going to go through the details of both situations for all three solutions, and we'll compare and contrast. Now in class I gave a rule, and that rule is that you can do a test. And the test is that you can compare the concentration to the initial concentration to the value of K. So in part A, you've got 0.10 molar, and you're going to divide by K, 1.0, 10 to the minus 4. And this is equal to 10 to the minus 1. If you're dividing times 10 to the minus 4, it's the same thing as multiplying 10 to the plus 4. And so this is equal to 10 to the third. This is greater than 100, so it's going to be okay to drop x. That's the rule that I gave in class. There are other rules, including a different rule that's given in your book. So for part B, the solution is 0.010. You want to compare that to the same K, 1.0, 10 to the minus 4. And this again is going to be equal to 10 to the minus 2. And then dividing by 10 to the minus 4 is the same thing as multiplying 10 to the plus 4. So this is equal to 10 squared. And if you remember the rule I gave in class, if it's greater than 100, it's okay to drop the x in the denominator. In this case, it's equal to 100. We're going to say it's okay, but we'll also admit that we're not 100% sure. So we definitely want to check on that one. Then for part C, the solution becomes even more dilute, and we're comparing 0.0010 to 1.0 times 10 to the minus 4. We get 10 to the minus 3 in the numerator, and multiplying that times multiplying times 10 to the 4th representing the denominator, and this will be equal to 10 to the power 1. So this is 10, and this number is less than 100, so it is definitely not okay to drop the x. So that's the rule I gave, and now on the next page we'll start the details of the analysis for the 3 solutions. So we're going to do both ways. And for solution A, we have 0.10 molar, and the issue is the equation 1.0 times 10 to the minus 4 being equal to x squared over 0.10 minus x. And first we're going to drop x. Okay. And if we drop x, then we have 1.0 times 10 to the minus 4, and that'll be equal to x squared divided by 0.10. And then x will be equal to the square root of 0.10 times 1.0 times 10 to the minus 4. And x will be equal to square root of 1 times 10 to the minus 5, which is equal to 3.2 times 10 to the minus 3. So this is our first result. Okay, now we're going to go back and solve the quadratic equation, and takes up a little bit more room. We'll start it on the next slide. So this is still part A. So we've got 1.0 times 10 to the minus 4 is equal to x squared divided by 0.10 minus x, and we'll have 1.0 times 10 to the minus 4 times 0.10 minus x is equal to x squared. And then we'll have 1.0 times 10 to the minus 5 minus 1.0 times 10 to the minus 4x, and that'll be equal to x squared. And then, I guess I had a parenthesis there. Then you put it all on the left hand side, you have x squared plus 1.0 times 10 to the minus 4 x, and then minus 1.0 10 to the minus 5, and that will be equal to 0. Then we're going to use the quadratic equation. X is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. We're going to plug in x is equal to negative 1.0 10 to the minus 4 plus or minus the square root of 1.0 10 to the minus 4 squared minus 4 times 1 times c, which is negative. Let's see if I can move this over here. Hang on. Just a little bit. Negative 1.0 10 to the minus 5. Those parentheses right there. And then we're going to divide by 2 times 1. And we're going to take the positive combination. When we get through that, we're going to have x is equal to 3.2 times 10 to the minus 3. Okay, so this is the answer using the quadratic equation. This is the true answer. And now we want to compare that to the answer that we got on the last page, which is what we would get if we had dropped x. And if you go back and look, you see that you get the exact same answer. So for the part A, drop x, we got x is equal to 3.2 times 10 to the minus 3. And if we included x, or didn't drop it, we got this exact same answer, 3.2 10 to the minus 3. So the difference between them, 3.2 10 to the minus 3 minus 3.2 10 to the minus 3 is 0. We compare that to the value of x, and it's 10 to the minus 3. Multiply that times 100, and you get 0%. So there is no difference, no error, and it's absolutely okay to use our test, which said it was okay to drop because the initial concentration over K was greater than 100. But then if you compare the two calculations written out, you see that there's absolutely no difference whatsoever. All right, it's a different story when you... And so with part B, it's a more dilute solution. So it's 0.010 as opposed to 0.10 in the last example. And you would set it up the exact same way. You'd have 1.0 times 10 to the minus 4 equal to x squared divided by 0.010 minus x. And it's the same question here. Can we drop this x or not? So we're going to do both ways. The first way, we'll just look at dropping x. And when we do, we've got 1.0 times 10 to the minus 4 is equal to x squared over 0.010. So x will be equal to the square root of 0.010 times 1.0 times 10 to the minus 4. So that's 10 to the minus 6. The square root of that is 1.0 times 10 to the minus 3. So that's what you get if you drop the x. All right, then on the next slide, we'll look at the details of not dropping x. So this is part B. Do not drop x. Okay, so then we have 1.0 times 10 to the minus 4 is equal to x squared over 0.010 minus x. It's a little messy there. And so this ends up being a quadratic equation, a lot more work. 1.0 times 10 to the minus 4 times 0.010 minus x is equal to x squared. And then this would be 1.0 10 to the minus 6 minus 1.0 10 to the minus 4x. And that'll be equal to x squared. Put it all on one side. You got x squared plus 1.0 times 10 to the minus 4x minus 1.0 10 to the minus 6 equals 0. Then you've got x is equal to negative b plus or minus b squared minus 4ac divided by 2a. You've got x is equal to negative 1.0 10 to the minus 4 plus or minus the square root of 1.0 10 to the minus 4 quantity squared minus 4 times 1 times negative 1.0 10 to the minus 6. And then all that's divided by 2 times 1. When you work that out, take the positive solution. And here the answer is 9.5 times 10 to the minus 4. So it's almost 10 times 10 to the minus 4, which is 1 times 10 to the minus 3, which is the answer that you get if you drop x. So what you want to do now is compare them, and we'll look at the difference. So we say 9.5 times 10 to the minus 4 minus 1.0 times 10 to the minus 3. So it's the true value minus the value you get if you're going to drop x, divided by the true value minus 4, times 100, and this works out to be 5.3%. So your book talks about this, Tro's book, and how 5% is pretty much the cutoff number. So if it's around 5% or higher, then there's too much error associated with dropping x. You're not getting values that are accurate or precise, and so in this case, you can probably get away with it. It's 5% error, but anything higher than that you probably want to worry about, and that'll be seen in the next example. Part. So for part C, then we're looking at the concentration of 0.0010 molar, and we have 1.0 times 10 to the minus 4 is equal to x squared divided by 0.0010 molar minus x. So again, can we drop that 0 or not? And we'll first look at dropping x. Let's just try it and see. And then that would give us 1.0 times 10 to the minus 4 is equal to x squared divided by 0.0010. X would be equal to the square root of 0.0010 times 1.0 times 10 to the minus 4. So that's 10 to the minus 7, square root of 10 to the minus 7, 3.2 times 10 to the minus 4. So this is the answer we would get if we tried dropping the x. And then on the next, we're going to look at the case where we do not drop x for part C. And now we've got, let's see, here we go, 1.0 times 10 to the minus 4 is equal to x squared divided by 0.0010 minus x. Now we have to multiply it out. 1.0, 10 to the minus 4 is multiplied times 0.0010 minus x equals x squared. So this is 1.0, 10 to the minus 7 minus 1.0, 10 to the minus 4x is equal to x squared. Put them all on the same side, put them on the right. So you have x squared plus 1.0 times 10 to the minus 4x plus 1.0 times 10 to the minus 7 equals 0. And then we're going to say x is equal to negative b, 1.0 times 10 to the minus 4 plus or minus the square root of 1 times 10 to the minus 4 squared minus 4a, and c is 1.0 times 10 to the minus 7 divided by 2 times 1, and we get here x is equal to 2.7 times 10 to the minus 4. Alright, and by the way, you need to work out the quadratic equation, punch the numbers into the calculator yourself, and make sure that you know how to get these numbers. It gets a little confusing sometimes. And also I can see a mistake that I made here. Let's see. So this is minus 4ac, and this is supposed to be negative here, sorry. And that's negative, so negative times negative is positive. You're actually adding the terms in the square root. But the answer's right. I had it right in my notes. Okay, so then let's go ahead on the next slide and compare numbers. So the true value is the one you get from the quadratic equation. So it'd be 2.7 times 10 to the minus 4. And then you get, what was the number before? It was 3.2 times 10 to the minus 4. And then you're going to divide it by the true value, 2.7 times 10 to the minus 4. Multiply it times 100. And you get, if I calculated this right, you get 18.5%. So this is way past 5% error. 18% error is completely unacceptable. And so you can see when the solution is becoming more and more dilute that the error is getting much, much higher. And basically every molecule counts. And you have to make sure that you include x. You have to work out the quadratic equation for the very dilute solutions. Alright, that's the end of the video. Hopefully you saw it in terms of the mathematics as to the differences between the two. I know there's lots of questions on it. Thank you.